Okay, we're going to work out this problem. And this one has a lowercase e for its voltage. We did a problem last time where we had a capital E voltage of 40 volts at an angle of 0 degrees. This one has a lowercase e, and this lowercase e is equal to the square root of 2 times 50 times sine of 2 pi times 1000 t. So I'll explain what these values mean before we get started with this circuit. The square root of 2 is another way of saying RMS voltage. The root means square value. The 50 volts is that's our RMS voltage. This is actually 50 volts at an angle of 0 degrees. We'll rewrite the circuit and set that as E. We're using the sine function for the sinusoidal part of this equation. The 2 pi represents a full circle, or the whole amount of radians, and then we got 1000 hertz per second, so or 1000 hertz. So that's 1000 counts per second. So this is what we'll use to find out what the x of L's are and x of C. And we rewrite this so that we have a more simpler equation. And I'll rewrite these as blocks. First, let's find the x of L's. We have x of L1, and that's going to be equal to 2 pi f of L1. Okay. So to make this a little more simpler, let's just take 2 pi times 1000. 2 pi is 6.28 times 1000, 6280, I believe. $62.83. So we can say that 2 pi f is equal to 6283 hertz. Where the only units we have here is hertz, so 2 pi. Now if I take that value and I multiply it by 0.1, well, we get 628. Well, I'll just write the equations here, and then when we get on the big board, I'll actually do the math. But I can do the math now so that I have it a step ahead. All right, so x of C, that's going to be 1 over 2 pi f of C. I'll redraw the circuit. Probably a couple times, because there is some series and parallel combinations in this circuit. C1. Z2. I took R1 in series with L1, added them together. I took the parallel combination of C, x of C, and x of L2, created it to be Z sub 2. So Z sub 1, that's equal to R1 plus x of L1. And then Z sub 2 is equal to x of C in parallel with x of L2. This can be rewritten as x of C times x of L2 divided by x of C plus x of L2. And then now we have Z1 in series with Z2, which is real simple. redrawing the circuit. I think we have a negative and positive. Yeah, we do up here, negative and positive for reference points for initial calculations. And we can just bring one more element here and just make that ZT as total impedance. And ZT, that's Z1 plus Z2. So that's how we're going to solve this circuit. And then we'll do the next one on the big board with math. Okay, so now we're going to do the math on these problems. Although we did 2 pi f, which is 3.14 times 1000 hertz. That was equal to 6283 hertz. All right, so let's calculate z sub 1, or x of L1, first of all. X of L1, need that first. And so that's notice I'm putting it in phasor form. I could write it in rectangular form. If I did, it would just be plus J628 ohms. But I like it in phasor notation because depending on whether we're going to do addition or subtract, addition or multiplication depends on which. If I'm going to use this to do multiplication next, I want to keep that in phasor notation. But since I'm going to add it to R1, it's best to put this also in rectangular notation. Phasor notation, rectangular notation. So this is x of L2, same thing. This one's going to be 0.2. And I don't want to make an algebraic mistake calculating that in my head. And it did turn out the way I thought it would. 1256. Which is the same here. Yep. Oh. Yeah, 1256 ohms at an angle of 90 degrees. And then when we do the x of c, I'm not saying C1 because there's only one of them here. So, and there's no other subscript with the x of c, like x of c, AB, kind of like the voltage drop we have between R1 and L1. That's just a particular voltage between A and B, and that's going to be between R1 and L1. And that measurement will be done last. One of the last problems we do because we already combined them with that the first redraw, which is Z1. And we got to go between there to find that. So we got to find Z1 first and everything else before we can jump back and we can still build the circuit and measure it, but we want to actually theoretically calculate what that voltage would be when we measure it across it. Now I could write this 1 divided by 2 times f of c. I like to write it this way. Put parentheses 2 pi f of c and raise it to the power of -1, which means it's the inverse of this. That way you don't have a rational expression, which means you have something in a denominator and then a numerator. So and our capacitor, 1 microfarad, which is 1 times 10 to the -6 farads. And notice I kept these in parentheses to, I try to, it's good for me to separate the magnitude with the units from each other so that you can see the product of them being distributed. Also, with phasor notation, you have magnitude and direction, and so keeping those in parentheses like this, it really helps when you see the product of the two values. But this value, I got to calculate this on my calculator. 6283 times 1 times 10 to the power negative 6. And we get 6.28. Oh, I forgot to take the inverse of it. 159.2. I'll just say 159 ohms at an angle of negative 90 degrees. Okay. So now that we know what all of our elements values are in ohms, now we can find the total impedance in ohms. So Z sub 1 is R1 plus X of L1. And this is going to be equal to, let's see, R1, 300 ohms plus J of X of L1, 628. Notice I wrote the ohms on the end here so that I don't have to put both of them next to the numbers. I could do that. It's just a simpler step. Let's see. 300 squared plus 628 squared, which is the Pythagorean theorem. If you watched earlier videos on these, you'll see how I demonstrated the proof on that step, part of the proof. So this becomes 696 ohms. The angle is going to be the ratio between the inverse tangent of the ratio between 628 and 300. It's always magnitude of reactance over magnitude of resistance. 64.5 degrees. All right, so that one is complete. Just go ahead. I'll edit it out.
I'm sorry.
I gotta edit your cat's meowing out too, anyway.
Sorry, I didn't realize you were.
Well, I've already got 2 videos posted online with some of these problems, these complicated ones. And I figured I'd jump to the hard ones first so that I'm not showing all the easy shit, first. I'll just backtrack that stuff.
Sounds good.
Okay, so now that we got Z1, now we're going to find Z2. And it's X of C in parallel with X of L2. So X of C times X of L2 divided by X of C plus X of L2. Now, this is going to be equal to X of C. We got X of C, 159. Now, I'm writing the units here just for habit. Right there, I just write the units there as a habit. Because I want to show that these are going to be distributed. I could have just left it out, but it's better to show the proper notation when it comes to phasors. It's much easier, for me it's much easier to see. Notice, if we add these two together, it becomes 0 degrees. We end up with a resistive value here in the top half. So X of C plus this, well, this is a negative 159 and a positive 1256. So this is negative J of 159 plus J of 1256. So 1256 minus 159. Well, this is going to be equal to, I'll put it over here, 1097 And that's positive, so we're at an angle of 90 degrees. 1097 ohms. Now this top half, we just do the product of 1256 and 159 and 199,704. This is ohms squared. We did the product of the ohms too. We always do the product of the units, the value, the magnitude of the value, and we take the product of the units as well. When it comes to phasor notation, when we do products, we always add the magnitudes of the phase angles. Sometimes it's not always 0 degrees. If these values were different, we get something different. But this is going to be at 0 degrees. And if we take that value divided by the 1097, 182 ohms. The ohms squared divided by ohms makes it ohms. And then 0 minus a 90 makes it negative 90 degrees. So this becomes a capacitive load in the end for Z2. But we're going to add Z1 and Z2 together. We know what this is because we just calculated it there. We know what this is because this is just a capacitive load. We could subtract this value from this, and now we have ZT. This is also equal to negative J182 ohms. So ZT, we got Z1, 300, and there's no, let's just say plus 0 for the reactance value. And here we have no reactance for the resistor, but we have this value for, oh, I'm sorry, we do have one for the resistor. We have 628. And that's going to be subtracted from the one, that's going to subtract the 182 from it because this is the capacitive load. 628 minus 182 is 446. So the total impedance becomes 300 plus J of 446. Okay, so let's do the Pythagorean theorem to find out what the total magnitude of that is and the phase angle. So 537. $56.1 degrees. Okay. Now I'm only doing this to 3 significant figures. The answers might have it to 4 significant figures, but if I round it to 3, it's most likely, because this is 556.07, but I rounded it up to 3 instead of using 4. This is the first problem they want us to solve, is the total impedance. Now they want us to find the source current, but we know what the source voltage is. It's 50 volts at an angle of 0 degrees. We don't want to use the value in phasor notation. We want to use that 50. So the IS, which is the source current, is equal to E divided by Z sub T, and that's 50 volts at an angle of 0 degrees divided by 537 at an angle of 56.1 degrees. We know what the angle is going to be. It'll be negative 56.1 degrees. And when we find a current, we get 93.1 milliamps at negative 56.1 degrees. So now that we have the second solution, we have this total current. there's 6 things they want us to find in this problem. The next is going to be the currents I1 and I2. Now, there's no solution in this book. It just shows the answers in the back. So, they want I1 and I2. They want to find the voltages V1 and VAB. V1 in this problem is the voltage across the X of L2 or L2. And that's I2 as well. Which is funny because you would think that V1 would have I1, but no. I2 is the current flowing through the source of where V1 is measured across. The capacitive load is I1 that we're going to find. We're also going to find the average power delivered to the network and the power factor of the network and indicate whether it is leading or lagging. All right, so this is A, this is B, and C, current through I1 and I2. The current through I1 is going to be the current through the capacitive load. Since we know what the total voltage is across ZT, we could find the voltage across Z sub 2 by using voltage divider formula. So up here, well, let's do it down here because E, let's say that the voltage at Z sub 2 is equal to E Z sub 2 over Z total. I take 50 times Z sub 2, 182. We get 9100 at negative 90 degrees. But let's do the whole calculation. Z sub T is 537, so divide that by 537. And the voltage across Z sub 2 will be 16.9 volts. And Z sub 2 is 56.1 degrees. So this negative 90 minus 56, it becomes negative 146. Negative 146 degrees. Now we know what the voltage is across Z2. We know what the current's going to be through X of C, because the voltage across Z sub 2 is the same voltage for X of C and X of L2, because they're in parallel. They share that same voltage from the top of that point where we're measuring to the ground point. Voltage measurements are always with respect to ground, unless it's written otherwise. And the respect to ground always is 0 volts. Let's take that voltage of 16.9 and let's divide that by what our X of C is, 159. That's how easy it is to find the current. You just basically you write your solutions down on a board or paper, and you backtrack to find what value you're using. I want to divide that by 159. 106.6. Let's just say 107 milliamps. So the current I1 is equal to E Z sub 2 divided by X of C. That is 16.9 volts at an angle of negative 146 degrees divided by x of c, which is 159 ohms at an angle of negative 90 degrees. A current 107 milliamps at an angle of, well, it's negative 146 plus 90. So we got negative 56 degrees. This is the answer for part C1. And I2, well, if we know what the source current is, we in DC we could just do addition and subtraction to find out what the difference is. Because we have different phase angles, we're going to have differences in values of current. So I can't just do that add and subtract here to find out what the difference is with the other one. Because this is its total source current, but this current through the capacitor has much more current magnitude than it does this one, the source current. They both have the same magnitudes of direction. So I2, we can find I2 because I2 is the current flowing through V1. And we know what X of L2 is, so let's just do that. We know what this voltage is, so I2 is 16.9 volts at an angle of 146 degrees, and that's divided by X of L2. We calculated that to be 1256 ohms. And that's 90 degrees because it's an inductor. 16.9 divided by 1256 at 13.5. We got 13.5 milliamps at an angle of, well, that's going to be negative 146 minus 90. That's negative 236 degrees. Right. Negative 146 minus 90. Right. So this is our I2. Now let's see what they want us to find. Find a voltage of V1. Well, we know what V1 is. That's V1. EZ2. 16.9. I'll just put a box around that as well, because that's one of our answers. Find the average power. Well, we know what average power is, right? We know what power is equal to in terms of Ohm's law. E times I, or V squared divided by R, or I squared times R. If you look at the Ohm's law relationship, you can find out how that's equivalent. Because IR is V, and if you take one of those I's away, you still have an I left, so that V times I is right there. Same relationship here. But we're talking about average power, and that's EI times the cosine of the difference in the angles between the voltage and the current. Well, we have that already. We got the total current. We know what total voltage is. Let's see, 50 volts, angle 0 degrees. And our total current, IS, 93.1. At an angle of negative 56. Well, the angle will be easy to remember and find out. Now let's go back to the original value of current, total current. Because I didn't save it. And multiply it by 50. 4.66. Oh. Whoops. Now, I shouldn't have wrote it this way. Let's do 50 volts times 93.1 milliamps times the cosine of 0 plus negative 56, 1 degrees. That's equal to 4.66 times the cosine. Oh, sorry. That's voltage times current. That's watts times the cosine of negative 56.1 1 degrees. So I take that and I take the cosine of negative 56.1 and I'm left with 2.6. 2.60 watts. And I did it to 3 significant figures. So